Hello everyone. So we'll be continuing from where we left off in the last lecture. In the last lecture, we looked at the integral form of the continuity and the momentum equations. Now we will use those equations to derive jump conditions at an interface. Now let me first explain what I mean by an interface, what is an interface in reality, and how we are going to mathematically set up this problem to determine the jump conditions. Now, let's start with a simple, as a canonical example, let's consider a simple air-water interface. Now, what we have is an interface separating two fluids, air and water. So when I say air-water interface, what we really have is if we zoom in very close to the interface, then we will have a small region which is very close to the interface. Where in this region, in the shaded region that I'm showing here, water and air will coexist. So what we have above that region is an air-rich region, and just below this interface, we have a water-rich region. So you can actually say an interface, it's an interface separating the water-rich region from the air-rich region. Okay. Now we can also examine how do properties such as density vary across this interface. For example, if I were to look at this interface and then identify this region, coexistence region, then typically what will end up happening is if I can make a plot of, let's say, density. Okay. Density here in this case is density is 1. This figure is not to scale. Density is 1 kilogram per meter cube. This is the density of air. And somewhere here is density of water is, let's make density of water with a different color. Density of water, let's say, is 1000 kilogram per meter cube. Okay. So what I mean by water-rich and air-rich region is, if I were to plot the properties of density of water, so density of air, it will be by and large constant here. And then the density will basically approach 0. So this will be the plot of the density of air. And similarly, if I were to plot the density of water, then it's practically 0. It's practically constant here. Then it will rapidly decrease here. And then it will be 0, right? So now, using both of this information, I can now I can come up with a general plot of the medium density. The average density of the medium would be, it will be 1 here, and then largely follow this curve. This will be, if I think of it as a single fluid with continuously variable properties, this is how the properties would look like. Okay. Now the only catch is that this region, the thickness of this region is order of few angstroms. It is so small that in the continuum regime, it is practically an interface for us. So we work in the continuum regime. And this means that the interface is really a mathematical surface. Okay. In other words, 0 thickness. I can assume that the interface has 0 thickness. Okay. Now, but can I use this information? Can I use this picture that I've painted for you, where there is a water-rich region and an air-rich region, and a region where water and air coexist? This picture that I've painted for you, Can I use this framework to derive the jump conditions at an interface? And the answer is indeed yes. So let's start with an interface which is actually not a mathematically zero thickness surface, but a surface of it's a region of finite thickness. So I'll just consider a small interface here, some arbitrary surface. There's an arbitrary surface. Obviously, it has two thicknesses. Now, I don't want to necessarily develop this framework with air and water in mind. So it could be any two fluids. So let's say above the upper surface, I have fluid 1, and below the below surface, I have fluid 2. So this is two different fluids, fluid 1 and fluid 2. And I want to take a small region on the surface, and this region basically goes from the upper surface to the lower surface. Okay, this region for me is a region of surface area S, and it's a small cylinder of length L. It's a small volume that I've considered, which looks like a tiny cylinder with surface area S, but it extends all the way across the thickness of the interface. So here for me, the thickness of the interface is L. Okay, so let me magnify this drawing that I had here. So here's I'll draw the cylinder in the horizontal way. This is my cylinder, right? So on one side of the cylinder, I have region 1. On the other side, I have region fluid 2. So I can now define normal vectors. So there is a normal vector at each point. So for example, the normal vector in region 1, let's call it as n hat with a subscript 1. Similarly, there is a normal vector on the other side as well, which is n2. And by definition, if you see that the thickness of the interface is really small, then you can essentially say that n1 is minus of n2 or n2 is minus of n1. And let's not forget that the thickness of the cylinder is of length L. Okay. So the system that I have now is I have an interface here between two fluids. This is region 1 and this is fluid 2. And any property, let's say it could be the density, it will vary smoothly from region 1 to region 2 over a distance of L. Okay, this could be any property, it could be density as an example. Okay, so this interface further can have a velocity like what we had. This interface need not be stationary, it can be moving interface. So let me just write down what we wrote in the last lecture. Let the interface have a velocity w bar. This is in the normal direction. So when I say the interface is moving, it is moving normal to itself. Therefore, w is the normal velocity of the interface. Okay. So we have already derived the integral form of the continuity equation. Let me just write it again here for completeness. Okay, d by dt of dv, rho dv will be minus ni rho ui minus wi ds over an arbitrary region. Now I want to write this integral over this arbitrary region, over region over regions 1 and 2. Okay, so now I have, if I consider for the small element that I have here, there are two normals here. So let me write down. So let me start by writing down for region 2. Okay, Ni rho ui minus wi ds. Then I have region over region 1, Ni rho ui minus wi ds. Okay, and then I have minus integral Ni rho ui minus wi ds over the curved surface. So basically, I'm saying that this cylinder has three parts. Okay, there is a part of the cylinder which is facing into fluid 1. There is a part of the cylinder which is facing into fluid 2, but there is also a curved part of this tiny disc or cylinder. Okay, and that's the contribution from this curved part. Okay, now what I can now do is I can write down the expressions for each of them, but we will remember that, recall that Ni in region 2 is minus Ni of region 1. That's what we wrote down here. N2 hat is minus of N1 hat. So I can now substitute this. I have d by dt of integral rho dv over the arbitrary region will be minus of minus Ni hat rho ui minus wi ds. This is over 2. Okay, then I have minus Ni hat rho ui minus wi ds. Okay, this is over region 1. Okay, and then I have plus, or rather minus, integral over something over the curved surface. Okay, now what we can do is we can take this tiny disk that we have and shrink its volume to 0 thickness. When I shrink the volume to 0 thickness, in other words, I'm saying that this thickness L that I have here, this L that I'm trying to highlight now, this L goes to 0 thickness. So if L goes to 0 thickness, you go from a cylinder with two different surfaces, one facing into A and one facing into 2, into a single surface. Okay, mathematical surface of 0 thickness. Okay, so now we have, if we shrink the interface to 0 thickness, that is, if I say that L goes to 0, then straight away you can see from this integral, the left hand side is a volume integral. Volume or integral of volume. What is the volume here? This is the volume inside this small tiny cylinder. But the volume itself is going to 0. Okay, so LHS goes to 0. Why does it go to 0? Since the volume dV is nothing but the length times ds. Okay, and therefore I have left hand side is 0. Okay, therefore I can now basically take okay, in addition I have one more important step. Also, the curved surface also disappears. And this immediately tells me that the integral essentially becomes integral over 2 rho ui minus wi ds is equal to integral over 1 rho ui minus wi ds. Okay, we have to know, don't forget the fact that ui is different in the two fluids and rho is also different. Okay, now since ds is arbitrary, we can directly equate the integrants here. What do we have? We have ni rho ui minus wi over region 2 is equal to ni rho ui minus wi over region 1. But you can also say, what is ni times ui minus wi? It is just n dot u, or that is nothing but rho times un minus w region 2 is rho un minus w over region 1. Okay, so this is basically the first jump condition here. Okay, I have to remember that the w that we wrote down here, w is already the normal component of interface velocity. So there is no need to put explicitly w subscript n, because w is already the normal component of the interface velocity. So this is a very important result. We'll call this equation star. Okay. So what is it telling you? That the densities, if the densities of the two fluids are different, then the velocities, the normal component of the velocities are also different. Or in other words, you can actually say density in fluid 2 divided by density in fluid 1 is equal to the normal component of velocity at fluid 1 divided by the normal component of velocity at fluid 2. Okay. The normal component of velocities are not the same if the densities are different. Okay. Let's consider an example. Let's consider a flat, large body of water, okay, which is evaporation. There is some evaporation going, which is evaporating. Okay. And because it's a large body of water, for all practical purposes, you can say that the motion of the interface is practically zero. Meaning, when water is actually evaporating, the level of the water actually keeps coming down with time, but the change in the level of the water is negligible. So for all practical purposes, you can ignore the variation of the interface position. Then what we now have is, we have a simple relationship. Un rho for water is equal to un rho for air, or in other words, the normal velocity of the air to the normal velocity of the water is approximately rho water by rho air, which is approximately 1000. So it says that when evaporation occurs, the water vapor travels at a speed of close to 1000 times more than the speed at which water is actually getting carried to the interface, because the densities of the two media are so different. Okay. So the first step that we have achieved in this calculation so far is we've derived the jump conditions for the normal component of the velocity at an interface. How did we do this? We did this by starting with the integral form of the continuity equation. Now we will derive we will start with the integral form of the momentum equation and derive jump conditions in interface for quantities such as stresses. Okay, so we'll start with the next part, which is jump conditions at an interface. And we'll use the momentum. Okay, let's write down the integral form of the continuity equation, the momentum equation, sorry. So this is something that was derived in the last lecture. So we have body force, then we have momentum flux at the boundary, and we have the stress term. So here sigma ij is the stress tensor. So for those who know, this is the stress tensor will be the pressure terms from the isotropic part plus the deviatoric stress tensor, where if it's a Newtonian fluid, the deviatoric stress tensor tau ij will be 2 mu times Sij, where Sij is the strain rate tensor. Okay, so now let's substitute this and we will use this definition of the stress tensor and simplify it a little bit. So we have Nj times sigma ij, then essentially becomes Nj minus P delta ij plus tau ij, that is minus P Ni plus Nj tau ij. Okay, and this is minus P in vector notation, it's P times N plus N dot tau. This is the last term of the momentum equation. Okay, now we will do the same setting that we have here. We have a volume, we have the same unit vectors. We will consider the momentum flux across this tiny volume that we have here, this cylindrical element that we have here, and we'll shrink the volume to 0. Okay, we'll start with this equation and we'll shrink the volume to 0. So shrinking the volume to 0, that is, as L goes to 0, we have the same thing here. All the volume integrals will disappear. So in the left hand side, that's a volume integral that will disappear. The body force term also disappears because the volume enclosed in the shrinking volume is 0, practically 0. So the body force term also disappears. Now we only have the surface forces. Let's write this down. So we have left hand side is 0, right hand side the body force term 0. Then I will again split this region into two parts. Again, I'm not explicitly writing down the area of the curved surface because the curved contribution of the cylindrical element is also 0. So only the two faces, which is a face which is facing into fluid 1 and the face facing into fluid 2 will contribute, right? So we have over 2, fluid 2, I have rho times. Now I make use of the fact that the normal vector is of opposite sign than fluid 1. So this is minus Nj, Uj minus Wj, Uids. That's the first term. That's the momentum flux. Then I have to write down the stress term. So I have plus the surface integral over facing region 2. I have minus nj times minus p delta ij plus tau ij. Now I'll write down over region 1. I have the same thing now. The only difference is that there is no minus sign. So there's a small correction here. There is no minus here. Nj minus p delta ij plus tau ij ds. Okay. Now I can combine terms of similar nature. So let me first combine all the terms over region 1 and region 2 and take it to two sides of the equation. So let's start by writing down a single equation over region 1. What are the terms over region 1? If I take it to the left hand side, I have rho nj uj minus wj plus nip minus nj tau ij. These are the terms over region 1, and this will be exactly equal to same terms over region 2. That is rho nj uj minus wj plus nip minus nj tau ij ds. Right? Now, because the integral again is arbitrary, I can directly equate the two terms inside the integral, and therefore I have rho nj uj minus wj this is over region 1. This quantity will be equal to over region 2. Right? Now, if you notice this is the vector equation. Okay, I can also write this in vector form. I have forgotten a ui here. Please add this ui. If I write this in vector form, I have this plus n hat p minus n dot tau over region 1 This is the vector equation because in every term I have exactly one vector, and this is over region 2. Okay. Now this equation is easy to analyze if we actually look at them in individual components. Okay. So what I have now is an interface. I have a small region here. Okay. And on that region I have a normal vector, and I can have I have a normal vector, and I can have two tangent vectors. All right. So we will also label this equation. We'll call this as equation double star. Okay. So the first step in this equation is we look at the velocity. What we have the bound. We can derive the boundary conditions from these equations or jump conditions of this equation. So let's start by looking at the first jump conditions at an interface. Okay. Now the first thing is that let's look at the tangential components. Now, just like no slip is an empirically observed fact for the fluid flow, the boundary condition at a solid surface, which means that if a fluid is basically moving past a surface, macroscopically the fluid does not slip. The fluid obeys what is called as a no slip condition at a solid surface. Similarly, the fluid also obeys, two fluids basically flowing one over the other also obey a similar no slip condition at an interface. So in other words, we have the no slip condition at an interface, which means that the tangential component of velocities are the same. What are tangential components of velocity? It is this u dot t. It is the taking the dot product of the velocity of a fluid at the interface with the tangent to the interface. Okay, so that's the first observation. Now the second observation is, now we start with this equation, that is equation in the box. This is obtained from the jump conditions from the momentum equation. Okay, we will take a dot product of this equation. This is equation double star, as I've called it. Okay, we'll take a dot product of this equation with a tangent vector. This could be any tangent vector on the interface. What do we get now? We will take rho un minus w of u dot t. That's the first term, rho un minus w and u dot t. Then I have plus n dot t of p. That's the pressure term. Finally, I have n dot tau dot t. Tau is the deviatoric stress tensor. Okay, this is over region 1. Is exactly same over region 2. But if I say that if I've already defined the tangent component of the velocity as u dot t, so this can be replaced with ut. Further, note that n dot t is always 0. They're orthogonal to each other. And so this equation essentially simplifies to rho un minus w ut minus n dot tau dot t two. Okay. But we also know from mass balance, the jump conditions that we have derived from mass balance, what we have already derived a simple relationship, which is density rho times un minus w over region 2 is same as un minus w over region 1. We have already derived this. Okay, this I'm going to show it here. This is rho un minus w over the two region across the interface is the same. Okay, and if I use this relationship, now the terms that I'm going to now highlight, this term and these two terms are exactly the same. Further, we also have one more. We also have shown that these tangential components are also the same across the interface because of no slip condition. So this entire term here, this term and this term, they are identical. They are equal across the interface. And therefore we have the above relationship just simplifies to n dot tau dot t over region 1 will be n dot tau dot t over region 2. Okay, n dot tau dot t, if you remember, is this extracts the shear stress. This says that shear stress is continuous across the interface. Okay, remember that all of this, the analysis that we are doing, is assuming that surface tension is not present. Okay, I'm first deriving the jump conditions across an interface in the absence of surface tension, and then we will introduce what are the variations to these equations in the presence of surface tension. Okay, so we have done the normal tangential component. How did we do the tangential component? We took the momentum equation, this equation double star, and then we dotted with the tangent component, tangential unit vector. Now we will analyze the normal component. Okay. We look at the normal component of star. Okay. The idea is exactly the same. We take dot product of this equation double star, which is the jump conditions, with n hat, and let's write down what we get. Rho un minus w times u dot n minus plus n dot n of p minus n dot tau dot n. This is across the region 1. At region 1 is same as the same expression at region 2. This is at 2. Okay. So we'll now simplify these expressions. Okay. So we can actually say, if you look at this expression, n dot tau dot n. Okay. Now we'll just give a simple shorthand notation, which will be tau nn. If you were interested in determining how to calculate this from a matrix notation, it will be something like nx, ny, nz. These are the normal components of the vector multiplied by the tensor tau. Okay, this will be a 3 by 3 matrix multiplied by nx, ny, nz. Okay, and this will give me tau nn. Okay, so now if I were to simplify this, I have rho un minus w un, which is the normal component of the velocity, plus p minus tau nn over region 1 is un minus w un plus p minus tau nn over region 2. Okay, so let's look at some special cases. This is the boundary condition that we have. Okay, there isn't too much of a simplification that we can do from here, but this is basically the jump condition across an interface. Okay, for a static case, the velocity, both the velocity of the fluid and the interface will be at 0. Tau will also be identically 0, and what you have now is pressure across the interface is continuous. Okay, so what we can conclude is pressure is continuous across the interface for a static fluid if, a big if surface tension is ignored. Okay, now what we are going to subsequently do is to derive these conditions in the presence of surface tension. Okay, so just to quickly recap what we have seen in this lecture is we starting with assuming that the interface is actually a region of finite thickness. Okay, we considered a small volume, a sheet of finite thickness. We considered a small elemental area on that of area S, and for this area S, it has three faces. We have one pointing into region 1, the other pointing into region 2, and then we have the curved part of the cylinder S. We wrote down the integral form of the momentum and the continuity mass balance equations or continuity equations for this particular volume element. We shrunk the volume element to 0 thickness, which means that in this particular figure that you can see, L was shrunk to 0. And when we did that, we derived a bunch of jump conditions. The first jump condition that we derived is that the normal component of the velocity multiplied by the density is continuous. Okay, so rho times un minus w is continuous. So if you say that the interface itself is not moving, then rho times the un is continuous across the interface. Okay, then we derive the jump conditions at interface starting from the momentum equation. Now the jump condition, because momentum is a vector, the jump condition also turns out to be a vector. So it is convenient to think in terms of individual components. So we can think of it in terms of just a normal component, a tangential component. To get the tangential component, we just took the dot product of that vector with the tangent vector, and we find that the shear stress is continuous across the interface. And I have to add a qualifier only in the absence of surface tension. We will see that even in the presence of surface tension, this term can still be continuous, but surface tension has to satisfy some conditions. Okay, and to get the normal component, we basically took the dot product projection of that momentum jump condition in the normal direction, and we found that for a static case where there is no motion, the interface is not moving, the pressure is continuous across the interface. Again, only if surface tension is ignored. So in the next lecture, what we are going to do is we are going to look at what is the role of surface tension and how do we modify these jump conditions across the interface in the presence of surface tension. That's what we're going to do in the next lecture.